All right, so following chain rule is what's called implicit differentiation. And I have already written down that implicit differentiation is finding the derivative for a function that cannot be written explicitly as y equals. So those are equations that might say something like y squared equals x. That's like a sideways parabola, or anything else that has y squared in it, or a variety of x times y situations such that the graph is not a function. So in this case, the graph is not a function. In that case, we can still find a derivative, but we have to find it implicitly instead of explicitly. I'm going to show you some examples and then show you how to work that. Okay, so right here is an example. You can see where this equation has y squared and even it's squared. There's no way to rewrite this, even if you multiplied it all the way out and make it y equals. There's a simple y here and a y to the fourth power. When you multiply this out, you'd have x squared, y squared. There's a lot going on here. And you can see the graph is definitely not a function. You could do a vertical line and cross it twice. But what we're trying to do here is decide that we could find the tangent line at this green line. It would have this sort of shape to it. In fact, here it is. So we can find derivatives and do tangent lines even though this is not a function. We just have to figure out how to take a derivative, and it doesn't fit the same rules as what we've learned so far. So we're going to work this problem and find the derivative and find this tangent line eventually. That won't be where we start, but this is what our goal is. So in this problem, you can actually see, because if we touch this twice, so in fact, right above that, this point, which is 3, 1, we have another point that's 3 something else. I'm trying to get Desmos to mark it, and it won't. But we could find a tangent line here, and it would be a completely different point. And we could find a tangent, it would probably be perpendicular right there. So what we're saying in these cases where we don't have an explicit function is that the derivative is dependent on the x value here, 3, and the y value. So this is the point 3, 1 versus the point up here, which is like 3, 2.7. So we need the x and the y value in the derivative, which is completely different than what we've done before. So let's see how we can do that. In my first example, this says, in notation, we've already learned d dx means, hey, take a derivative of x cubed. It's the same way if we said y equals x cubed. And this is an explicit equation. It's y equals. So it's already, everything over here is in terms of x. And so we're going to say that these variables agree. This is taking the derivative with respect to x, and this is all in x. So with respect to x, and this equation x cubed is all x. So we do this like normal. We take a power rule. We would say the derivative is 3x squared. But what we do when we take an implicit derivative, something like d dx of y cubed, note that this says take a derivative with respect to x, but this variable is y. They are not the same. We're going to call that variables that do not agree. In other words, they're not the same. All right? So when we take the derivative here, this is like chain rule. So when we do that, we're going to take the derivative of, this is supposed to be y cubed. It wrote really strange. But anyway, y cubed. When we take its derivative, we also get 3y squared. But now we need to take the derivative of y with respect to x. We need to chain rule it. So we need to chain rule this derivative with respect to x, meaning where it is with respect to x in the function. And we write that as dy dx. And we've always done this. but we've never written the notation out like this because we didn't know enough math to do it. So this is an implicitly defined derivative. If we look back at this one, our very first example, when we take the derivative of both sides, so we just took, in our first example, the 3x squared. X cubed's derivative is 3x squared. If we take the derivative of this side, if we take the derivative of y, we get 1, which I can write. And then we take the derivative of y with respect to x, and it looks like this, dy dx. In the first couple days of school, when we learned our first notation, dy dx was just given to you and you had to know that meant derivative. Now what we're doing is we're taking the derivative with respect to x in a new way. So the simple ones, we were doing this all along. You just didn't know it. But another way to rewrite this, instead of y prime equals 3x squared, is to say dy dx equals 3x squared, because this was in terms of x. Let's see some more. So in this example, the directions say, hey, please take a derivative with respect to x of x plus 3y. So looking at this, hopefully you notice that this first term is x and it's in terms of x, so it doesn't really have a chain rule attached to it. This one, 3y, is in terms of a different variable. The variables do not agree, and it will need a derivative with respect to x. It will need chain rule. So here we go. We learned with limit properties of derivatives, we can do these separately. So when I take the derivative of x here, I'm going to get 1. Now, some books and some teachers, so I just want you to see this, will say, hey, implicit's a little bit hard. What if I took the derivative of x with respect to x? What would I get? And that doesn't change your problem at all because this is still 1. I still have 1 there because dx over dx is 1. Now we take the derivative of the second piece, and we're going to say the derivative of 3y is 3. And then we have to chain rule it. We have to take the derivative of y with respect to x. Derivative of y with respect to x. So we get 1 plus 3 dy dx. Why? Because our function has x and y in it. So our derivative has to show that we're taking a derivative of x with respect to x and of y with respect to x. So this is our final derivative. Example 2 is very similar, but it's going to have product rule. So I've got derivative with respect to x of xy squared. So we're going to do first derivative of the second plus second derivative of the first. But whenever we take the derivative, we're going to chain rule it. So we're going to take the derivative of each variable with respect to x. So first is x times the derivative of y squared, that's the second, that'll be 2y, times the derivative of y with respect to x. Plus, because this is product rule, we have 2 terms. We're going to keep y squared, and now we're going to take the derivative of the first, which is 1, times the derivative of x with respect to itself. And I'm doing that to show you that it works to take the derivative of every single term, but you do not have to write this because it's 1. It's just y squared times 1 times 1. But I want you to see why it's 1 and why that's not necessary. It's just because this variable agrees with what we're taking the derivative with respect to. So our final look at this derivative would be 2xy dy dx plus y squared. Okay, we've had a little bit of practice. Now let's do a definite implicit equation. This one, even though I've written my y's weirdly, cannot be written as y equals. We can't just factor out a y and then solve for y. So this equation looks very interesting graphed, and we will look at it in a second. But we want to find the derivative. So there is slope. This is something that can be graphed. It's not a function. We can't actually graph it on our calculator, but we can graph it in Desmos, and I'll show you what it looks like. But we can also find derivatives for it. So let's do that. there's 1, 2, 3, 4, 5 terms. Within those 5 terms, the first, second, and third all have variables that disagree with derivative with respect to x. So each one of these will have a dy dx. This one will have a dx dx, and so you don't even have to write that one. And then this will take a derivative of -4 and we'll get 0. So here we go. Derivative of y cubed is 3y squared times the derivative of y with respect to x. The derivative of y squared is 2y dy dx. Derivative of -5y is -5 dy dx. Negative x squared is -2x. I'm going to write dx dx because we're still beginning here. And the derivative of -4 is 0. So we've taken the derivative of everything. What we want to have in our final analysis is dy dx equals. That's what our goal is. So what we're going to do is, I'm going to rewrite it just once so I can see it pretty. 2y dy dx minus 5 dy dx. And I'm going to put this cancels, so it's just 1. So I'm going to put this -2x on the other side equals 2x. So since my goal is to make it dy dx equals, I'm going to factor out all of these guys. So I'm going to have dy dx. And then parentheses 3y for the first term plus, 3y squared. I wrote that badly. 3y squared plus 2y minus 5 equals 2x. And then to get this by itself, obviously I need to divide on both sides. So here we go. dy dx equals 2x. And then 3y squared plus 2y minus 5. So we found the derivative. And if we plug in different x values and y values, we will find slope for any point on this graph. Any point is going to have an x value and a y value, but we need both to find slope. And we've not had that before. We've only had slope in terms of the x value. Now we have slope in terms of both. This is what that function looks like. And you can see it has a vertical tangent. Oops, I'm not writing. It has a vertical tangent here. It has a vertical tangent here. It has a horizontal tangent here. It has some sort of negative tangent here. And it has tangents everywhere. It has tangents all over the place. But it depends on what point, where you are on the graph. So at this point, 2, 0, it has a slope that's negative. But at 2, 1.8 or something, it has a slope that's increasing. So the slope is dependent on the x, y, both of them for our slope. Okay, let's actually find a tangent line and graph it on Desmos and see what it looks like. Let's take the original equation, which is y cubed plus y squared minus 5y minus x squared equals -4, and let's plug in 2. Okay, so let's say x equals 2. Oh, let's don't do that. That's too hard. Let's do y equals 0. So if y equals 0, that's really easy to plug in. So we're going to get 0, 0, 0. We're going to get -x squared equals -4. So x squared equals +4. X equals plus or minus 2. So when y is 0, we have 2 values for x. That means we have 2 points. We have the point 2, 0, and we have the point -2, 0. And looking back at my graph, we have 2, 0 and -2, 0. So that works out. Okay, so what does that mean? Well, that means that if I pick a point, let's say we're going to do this. Here's some new notation for you. If we're looking at dy dx, evaluated at the point 2, 0. So that's what this notation means. It means we're doing slope. Evaluated, that's this line at 2, 0. Then we're going to plug it into this derivative and see what we get. So we're going to plug in 2 for x. That'll be 2 times 2 over. and then 0 for y. That's going to be 0 plus negative 5. So slope equals 4 over negative 5. So this is the slope formula. This is slope, so I can call it m. And I can write my tangent line as y minus 0 equals negative 4/5 x minus 2. So I'm going to plug this equation into Desmos and see what that looks like. All right, so here's my graph on Desmos. Here's my point, which I can't draw on. If I draw in the line that we just talked about, here you can see the tangent line at 2. It was dependent on having the point. If we graph it over here, it's going to change the sign because of our equation. So if we plugged in negative 2 right here, we would get a positive slope. So we could have a positive slope for Desmos over here. Trying to make Desmos show up. There she goes. So if we typed in the same thing, y minus 0, and then 4/5, the positive slope, equals 4/5, and then x plus 2, because we're on the other side, you can see we've got a tangent line on the other side. So what does implicit differentiation do? It allows us to take derivatives of things that aren't functions, because what we end up doing is we end up taking the derivative in the middle of the problem. So instead of saying the derivative is the very first thing you write down, like y equals something, here I've got y equals x cubed right here, and saying, well, this derivative is going to be, instead of y, I would have dy dx. We're having to go over here and take the derivative in the middle of the problem. So we've got taking the derivative of y cubed and y squared and y. It's not just y equals. Each one of these has a dy dx. So y cubed has a dy dx. Y squared has a dy dx. Y has a dy dx. So every time you take a derivative of y with respect to x, you're going to have to write dy dx. And this is one step up from what we did before with plain simple product rule, power rule, quotient rule, chain rule, because those only had one y in the problem, and it was at the beginning of the problem. So now we're going to have them in different ways so that we can take derivatives of harder problems. Okay, for my next example, I've got a simple circle. X squared plus y squared equals 4. You should recognize this as a circle. It has its center at the origin, 0, 0, and a radius of 2. If we want to find the derivative at any point, so here's what the circle looks like. Right, so circle. If we want to find the slope here or here or here, or anywhere on the circle, we can see that it would have a tangent line, and we would take the derivative with respect to x. So dy dx is our goal here. We're going to take this derivative with respect to x, and the y with respect to x, and the 4 with respect to x, which doesn't change, so it goes to 0. So we're going to say that's 2x dx dx, and that's 1. We don't have to write it down. Plus 2y, and then dy dx, we're doing the derivative of whatever variable we took. That's the chain rule, and then derivative of a constant is 0. When we solve here, we have 2y dy dx equals, we put 2x on the other side, negative 2x, divide by 2y, and we get dy dx equals negative x over y. And this is a really fun one to do because it's so simple to see what the derivative is and what the tangent lines look like. So we could plug in and say, well, where are their horizontal slopes? Well, horizontal are where the slope are 0 And where this derivative equals 0 is where the top equals 0. So negative x over y equals 0 is going to be where x equals 0. And here we are, where x equals 0, you can see we have a horizontal tangent. Now, what does the y value equal when the x equals 0? So what this is saying is where x equals 0, the slope is also 0. That's what this statement says. We solve for x, and that tells us about slope. Now, if we want to find the points, we'd have to go back to the original equation, and we'd plug in x equals 0. So we'd say 0 plus y squared equals 4. We get y equals plus or minus 2, and we can see that this is the point 0 for x. Here's x equals 0, and y equals positive 2, and also 0, negative 2 from a plus or minus. And we can see this point and the other point, and we're good. Where do we have vertical tangent lines? Well, that's going to be where the slope is undefined. And that's otherwise known as where if we have negative xy equals slope, is where the denominator equals 0. So that's denominator equal to 0. And so when y equals 0, that's y equals 0, and x-intercept, that's here and here. And so definitely those lines would be tangent there. We can also plug that back into the original equation and say x squared plus 0 equals 4. So x equals plus or minus 2, and we have 2 points there as well. We have 2, 0, and negative 2, 0. And at those 2 points, we have vertical tangent lines. So we can do a lot with a simple circle, but we couldn't do this as a function before. Well, we could have made this one explicit. So we could have done this with a chain rule, but we would have needed to do it twice because we'd have to take the derivative with the plus or minus. And this is what I mean by that really quick. If we had made this explicit, we would have said y squared equals 4 minus x squared, y equals plus or minus the square root of 4 minus x squared, which would have meant we'd have to do the chain rule here because we really have two functions plus the square root. Actually, I'm going to go plus 4 minus x squared to the 1/2 power to use chain rule. And then I'd have to do the same thing with a negative on the outside. So I'd have to have two equations in order to go this way because we take the square root and get plus or minus. So implicit is used most often when you cannot make it y equals. Okay, now, do you have to be able to graph these implicit functions? So graphing this circle, even though mine's not pretty, graphing a circle is simple. Graphing other things is difficult. And so no, you don't need to be able to graph it, but you need to, the reason I've shown you graphs is so you have a framework for, okay, these aren't functions. I need both the x and the y value to be able to find the slope at a point. So you don't need to be able to graph. The graphs were shown for explanation. Okay, and so we're talking about any sort of crazy shape you can think of, something like this. We could find the slope at this point, or this point, or this point, or this point, and we do that because the derivative would have both some sort of x and y here, x and y would be in the equation for whatever this particular graph is. And then when we know what point we're looking for, this particular xy, we would plug that in to the derivative and be able to find the slope for this tangent line. We would have a different x value for over here, x2, y2. We would plug those in to the derivative and find the slope for this particular tangent line. Each x and y value would have its own slope. All right, so there you go, implicit differentiation. This is chain rule because you're having to take the derivative of the variable itself. So it's chain rule in the sense that if you see y cubed, you're going to take the derivative 3y squared. If we're doing y cubed prime, we're going to say 3y squared times the derivative of y itself, so dy dx. All right, thank you.